are X-rays generated? Classic X-ray sources consist of a tungsten filament and a metallic anode suspended in a vacuum tube. When electricity is run through the filament, electrons are boiled off. The electrons are accelerated towards the anode with a strong electric field. When the electrons interact with the atoms in the anode, two different things can occur. The first possibility is that the electron will change speed and direction due to the atom's nucleus, producing a broad emission spectrum known as Bremsstrahlung, German for breaking radiation. The second possibility is that an electron is knocked out of the atom. The hole is filled by a higher energy electron, resulting in the emission of an X-ray with a very specific energy. These are called characteristic X-rays, leading to characteristic radiation. This is what is used in X-ray diffraction. In addition to creating X-rays, a large amount of the energy is converted into heat, requiring the anode to be cooled. In the traditional tube, the large footprint of the wide electron beam limits heat dissipation, requiring the anode to be water-cooled. By using a small, spot-shaped electron beam, heat can be dissipated in 3 dimensions. These micro-focus sources allow the anode to be air-cooled and produce a very bright point-focus beam. The source intensity can be further improved by optimizing the takeoff angle. Tubes designed for non-destructive testing and imaging applications typically have a high takeoff angle, providing a wider spreading and even dispersion of the X-ray flux. As the takeoff angle is lowered, the beam intensity and energy focus increases. Tubes with low takeoff angles are ideal for single crystal diffraction experiments. Cooling could be further improved using diamond hybrid anodes, which benefit from 5 times greater heat conductivity compared to traditional copper blocks. The latest generation of these sources uses an isotopically pure diamond, which allows for maximum intensity of the source. Since diamond anodes can manage such high-intensity electron flows without the concern of overheating, traditional filament coils are replaced with new high-brightness cathodes. The combination of diamond anode and high-brightness cathode outperforms micro-focus rotating anode sources while keeping the benefit of low maintenance and a tube lifetime of 5 years or more in place. Finally, the current state-of-the-art microfocus sources incorporate electron optics that condition the electron beam. Focusing and defocusing occurs instantaneously, enabling the fastest wavelength switches between 2 alternate sources. Producing X-rays is just one part of a comprehensive solution. Takeoff angles optimized for the diffraction experiment, efficient optics, precisely controlled sample handling, large area photon counting detectors, and state-of-the-art software packages are all important in achieving outstanding results.